Okay. So today is our fifth session, right? Fifth. So we have 6 more to go. Yeah. Number 5 until number 10. Okay. So last week I was talking about the application of differentiation. Okay. And we finished at this rule called L'Hopital's rule, which is a rule allows you to work out the limits of some indeterminate form. Yeah. And to do that, of course, it requires differentiation. So this naturally form one of the important application of differentiation. Well, of course, we have a lot of application for differentiation. It's not possible to cover all of them. So in the textbook and also in my handout, it's only cover some basic one. I give you a wide variety of the possible application of differentiation. But of course, there are many other applications. The textbook or the notes cannot just exhaust all the possibilities. There are many other applications also. So I think today we should be able to finish all the applications of differentiation, hopefully. Hopefully we can finish all the remaining applications using differentiation. So the first one we look at is the minimum and maximum values. Okay? And I suppose most of you probably have done that before, but I mean, we are going to do it in a much more detailed manner to look into all the different aspects of minimum and maximum. Okay? Now, first of all, let's define what we mean by absolute maximum and also absolute minimum. So the word is absolute. All right? There are other type of maximum and minimum which I will define for you in a short while. But let's start off with this absolute maximum and also absolute minimum. I mean, absolute. The word absolute also imply this apply globally. What I mean is that it applies throughout the entire domain for a function. All right. So given a function, of course, given a function of course has its domain and range, which I talked about in the first lecture. So within a certain domain, if there is certain point, there is a certain point at x equal to c. All right. At x equals c, we can substitute x equals c into the function to find a functional value. And if that functional value turns out to be the largest for the entire domain, then we call it absolute. Okay, absolute maximum. On the other hand, if the functional value at the point x equal to c is the smallest within the entire domain, then we call it absolute minimum. Okay, I think it's quite simple. And of course, collectively, maximum and minimum collectively, we can call them extremum. Right? Extremum means extreme values, right? So either the largest or the smallest, both can be called extremum. So extremum can be either maximum or minimum. All right. And the plural for that will be extrema. All right. So maximum and minimum are singular word. Plural will be maxima and minima, just like extremum and extrema. All right. So this is a definition of absolute maximum and absolute minimum. It has to be either the largest or the smallest within the entire domain. So let's look at this example. I mean, just give you a little bit more pictorial explanation of what we mean by that. So if you look at the one on the left side, right on the bottom, this corresponds to a value of x equals c, right? And the corresponding value, f bracket c, the functional value at x equals c, is what we call absolute minimum, because for the entire range, you can see along the blue curve, this point happened to be the smallest value for the function. So we call this the absolute this point absolute minimum. On the other hand, a shape like this, an inverted U shape, then at this point x equals c, the functional value, the corresponding functional value attains the largest value for the entire domain, all right? And therefore, we call this the absolute maximum. Now, in these two cases, there isn't any, okay, for the first one, there isn't any absolute maximum, but for this one, there isn't any absolute minimum. This is only true when we consider an open interval, Now, if you still recall, open interval excludes the endpoints. Closed intervals include the endpoints, right? If these were closed interval, then we can have actually absolute maximum or an absolute minimum for the left and the right diagram respectively. But I mean, at this point, I will illustrate in another diagram, all right? So for these two cases, the interval or the domain is actually open, all right? Okay, just go through this very simple example. All right, so it's three of them. So we have this function x squared minus 9 for the three parts, and then it depends on the interval or the domain. The first one, the domain is the open one, minus infinity to infinity, and then part B, this is again another open interval from minus 3 to 3, but the last one is a closed interval from minus 3 to 3. So just repeat that again. The closed interval minus 3, we use the square bracket to denote this a closed interval. So that include the endpoints. That means x can be minus 3 or 3, right? Whereas the open interval minus 3 and 3 is the x value takes anything in between, but it cannot take the value right at the ends, all right? We call open interval. Likewise, part A is also, this one is also open interval. We use the rounded bracket to denote this open interval. Okay, so this is part A. So the function look like this, okay? I mean, we can sketch the function. It looks something like that. And then if we consider the open interval, that is to say we exclude the two ends, right? So we exclude the two endpoints at minus infinity and infinity. And therefore, for this case, it's just like the diagram you saw in the previous slide. There isn't any absolute maximum because the two endpoints are excluded. Okay? So within the domain or within such open interval, we only have one absolute minimum that occurs at x equals 0 at this point. So we call this absolute minimum. Okay? Okay, for part B, this is an open interval. All right, open interval, remember, this excludes the two ends at minus 3 and 3, and therefore at the two ends you can see we use a circle or an empty dot. Yeah? You can see the two empty dots or circles. This denotes the open interval, meaning that the two ends are excluded. Okay, so this, if you still recall what I went through with you in the first lecture. Okay, for this case, you look at it, of course, the shape is like that, and then since the domain or the interval is from minus 3 to 3, so it only covers this part of the curve, right? And by look at the diagram, you can see that we also have a absolute minimum, all right, at this point. So because this is the smallest within the entire range, and there isn't any absolute maximum. The reason is because this is an open interval for which the two endpoints are excluded. Now, what I mean by that, yeah, perhaps let me take you through part C, then you can have a better understanding of what this means. So the difference between B and C is that in part C, this is a closed interval, in that the two endpoints are included. So therefore, you see the two solid dots at the two endpoints, denoting this is a closed interval. Now, since the two ends are included, then we can have maximum at the two ends. At both minus 3 and 3, you can see within the whole interval, then at these two locations, x equal minus 3 and 3, the functional value is the maximum, yeah, within this interval. Okay, and these 2 points are included, therefore we can have maximum at these two endpoints. And of course, we also have an absolute minimum like the other cases. All right? So open interval, closed interval, there is a difference. So just a few more diagrams to show you the different scenarios. Let's say this one, the curve go like this, all right? And we are talking about closed interval now. So the endpoints are included, okay? Closed intervals. Okay, for this case, this curve go up and down like that. And obviously, the absolute maximum occur here because this is the largest value for the within the entire interval. This will be the absolute minimum, all right? So if you look at this case, so this is the curve, and since it's closed interval, so that the two endpoints are considered. So within the entire interval, one can see that the maximum, the absolute maximum, occur at this endpoint at x equal to a, and whereas at x equal to b, we have the absolute minimum. Should this be an open interval for this case, then we don't have any maximum or minimum. Right? If the endpoints are excluded for an open interval, then this maximum and minimum doesn't exist. Okay. Anyway, we are talking about closed interval in this diagram. So for this case, from A to B, A, B denote the interval, all right? So you can see the absolute maximum is on the top here at the peak, and then the absolute minimum will be down here at the left end point here. All right, because this is the smallest, takes the smallest value. And for this case, the minimum, the absolute minimum occur right on the bottom of the curve, okay? And the maximum occur at this end point on the right side, all right? So this is for closed interval. Let's say for an open interval, let's say the curve is a straight line, something like that, y equal to x. Then at the two ends, you see the empty dot there, or circle. So this is an open interval from 0 to 1. So in that case, we don't have any maximum or minimum because the two ends are excluded. Okay? There isn't any maximum or minimum in this interval. All right, so just give you a few more. Okay, so for this case, this interval is an open interval from minus infinity to infinity, so the two ends are excluded, and therefore, for this curve y equal to x squared, then we only have one absolute minimum here at the origin. Now, if we are considering a closed interval for the same curve from 0 to 2, closed, that is including x equals 0 and x equals 2, then we have an absolute minimum here and an absolute maximum there. For this case, one side is open, the left side is open, so this is an open end, this is a closed end, all right? So in that case, this open end, the point is excluded, so we don't have a minimum here, right? Because this point is excluded. But at the other end, this is a closed interval, so this end is included, and we do have an absolute maximum at this point. For this case, if both ends are open, just like the last diagram, you saw a straight line. So since both ends are excluded, there isn't any maximum or minimum within this interval, 0 to 2, okay, for open interval. All right, so this one is called the extreme value theorem. So if we have, you can see I went through with you many different scenarios, right? Whether closed interval, open interval, or maybe one side closed, one side open, that kind of situation. And you can appreciate this so-called extreme value theorem, which says that if we have a closed interval A and B, then we definitely will have absolute maximum and absolute minimum within a closed interval, or a closed interval. So you may ask, hey, what happened if situation is like that, a horizontal line, closed, right? So we have a two solid dot from A to B. Let's say this one, fx equal constant, right? It's horizontal line, but closed interval. Well, we still have maximum and minimum. It's just anywhere. You can take this point, it doesn't matter which point you consider. This point can be considered, any point can be considered as either a maximum or a minimum. In this case, the maximum and minimum are equal. All right? So this extreme value theorem just say that so long as you have a closed interval, then there definitely an absolute maximum and also an absolute minimum within that interval. So this is called the extreme value theorem. Therefore, if the function is continuous, then definitely there is, as I mentioned just now, there is definitely an absolute maximum or minimum. All right? Okay, let's look at this example. So we want to find the absolute extrema. So extrema means either maxima or minima. All right? For this function, 1 over x. And the interval, we have to define an interval for it. All right? So it's a closed interval from 1 to 3. And I think if you look at the plot here, you can see it's just one of the situations that I show you already, right? Of course, right here, what we can do is that we can refer to the extreme value theorem, which says that so long as you have a continuous function within a closed interval, there is definitely a maximum or minimum. You can see that the maximum, absolute maximum, occur at the left endpoint, and the absolute minimum occur at the right endpoint. Okay, and of course we can work out the value also. Since the absolute maximum occur at x equal 1, therefore the absolute maximum is 1. Whereas the absolute minimum occur at x equals 3, at which the functional value is 1 over 3. So 1/3 is the absolute minimum. Yeah. So a very simple example. It's just some idea. Okay. Now let's move to local. Yeah. Local extremum, which can be either be local maximum or local minimum. This is not absolute. Absolute, we are talking about the whole interval. Yeah. But this one we are talking about local. All right. So what we mean by local maximum and local minimum? So long as at the point x equal to c, the functional value is the largest. Right. At that point, when you compare with its neighboring value, I mean on the left side and on the right side of this point x equal to c. So if those values are smaller than the value at x equal to c, then obviously fc is large, right? And we call it local because it only greater than the value on the left side and on the right side at that point x equal to c. But it may not be the largest for the entire interval. So we do have the difference. Absolute is for the entire interval. Local is only around that point. Right? Around that point, if nearby, let's say if it attains the largest value nearby, then we call it local. So local can be absolute also in some cases. For example, if you look at this one, of course, just now we were saying that this is an absolute minimum, right? Well, we can also say that this is local because this is also the smallest value compared to the value nearby on the left side, on the right side, isn't it? So they both can be the same, but the only difference is that absolute require the value to be either the largest or the smallest within the entire interval. But local, no. For local extremum is we only compare with the values surrounding that point. Okay, so this is the difference between, of course, we call it local extremum. All right. So collectively, either maximum or minimum, we say they are just extremum. Okay, give you a diagram to show you what we mean by here. So if you look at this graph, something like that, it has got sharp corners as well, So at this point, x equal to a, we have a local minimum. This cannot be the smallest within the whole interval. The whole interval, you can see the entire curve, right? That's the entire curve shows you the entire interval. So this one, while this is the smallest value compared to the value surrounding this point, you can see that, right? It's a U shape locally in this region, right? But there are many other locations, let's say at this point somewhere here, obviously the value of the functional value is going to be smaller than this one. So this cannot be absolute, right? Okay, this one also a local maximum for the same reason. Only around this region, this is the maximum. But if you compare this with the value for the entire interval, this cannot be the largest within the entire interval. So we call it local. All right. So this one is a local minimum because it's larger than the value surrounding it. But we can also call this the global because this value is also the smallest within the entire interval. So this one is both local and absolute minimum. All right. This one is a local maximum for the same reason, and again for the same reason we can call this the absolute maximum as well because this is the largest within the entire interval. Okay. So sometimes a local can be absolute also. It depends. All right. Now, if you look at this diagram, you can see at these 2 points, obviously the curve goes very smoothly, right? It goes down, up, and then coming down, changing direction, all right? So at this point, x equals a and b, you can see that the local extremum occur when the tangent line is horizontal. If you draw a tangent line, it's horizontal because this one is changing direction, right? At that point, and therefore creating either a minimum or a maximum. So at x equals a and b, you can see that they occur when the tangent line at these points are horizontal. Okay? On the other hand, at the other 2 points, when we have sharp corner, then the tangent line is undefined. We can't draw a tangent here at a sharp corner, at these 2 corners, right? So at these 2 points, the tangent line is undefined, and therefore the derivative, the first derivative represents the tangent line, isn't it? So the first derivative at these points, x equals c and d, are undefined at these 2 points. So from this diagram, you can see that extremum occur either when the tangent is horizontal or when the tangent is undefined. That is, the f prime is undefined. Okay? So just bear in mind, extremum always occur when the tangent line is horizontal, so the derivative there is 0. Yeah? So f prime at these 2 points are 0 because the tangent line is horizontal. So, and also when the tangent line is undefined, for which the derivative, the first derivative of the function is undefined. So either the derivative is either 0 or undefined. Then we have this extremum, all right, can be maximum or minimum. Okay, just one more graph showing you the same thing, basically. Okay, so this is a closed interval. This one is closed interval. So the 2 endpoints are included. So this point, you can see this point is an absolute minimum because it's the smallest within the entire interval from A to B. This is local. This cannot be absolute because there are elsewhere at which the functional value is higher than this. All right, so this can only be called local maximum. Same thing here. We just go through the same thing one more time. So this is a local minimum. This one called absolute maximum. We can call this local also. So also a local maximum. All right. So this one is a local minimum. So I think now you should have quite a good understanding of what we mean by absolute and local extremum. Okay, let's look at this example. We want to locate any local extrema, all right, for this function, 9 minus x squared. So you know that local extremum occur either when f prime equal to 0 or when f prime is undefined, right? That is to say, either the tangent line is horizontal or the tangent line is undefined. So we always have to work out the derivative, isn't it? So that is where the application of differentiation comes in, yeah? Because we know that this only occurs either when f prime equals 0 or when f prime is undefined. So let's work out f prime. So differentiate this one, pretty straightforward. You get minus 2x. And then if you equate this to 0, then minus 2x equate the f prime to 0, then your minus 2x equals 0. And that will give you x equals 0. So in other words, at x equals 0, f prime will be 0. So therefore, you know that there is actually an extremum occurring at x equals 0. Well, whether this extremum is maximum or minimum, we don't know. We don't know. So long as f prime equals 0, it's definitely an extremum. It can be either maximum or minimum. So we don't know, right? From this f prime equals 0, we don't know. But this graph, if you look at the graph of this function, which can be plotted quite easily, it goes like that. You can see that this one actually is a maximum, a local, of course, yeah, local. All right, because just now I was saying that local extremum occur when f prime equals 0 or undefined. And of course, later on, I'm going to show you how to determine whether the extremum is a maximum or minimum. Okay, and also how do we work out the absolute extremum as well as local extremum. All right, but for the time being, let's look at the curve. Then we see, this is a maximum. Okay. Now this one shows you f prime is undefined. All right. Now the function is an absolute value of x, and the curve goes like that, absolute value. All right. So there isn't anything below the xy plane on the lower half of the plane because absolute value meaning that it must always be positive. So this is the graph. I think I showed you this graph of the absolute value before. Yeah. When I talk about absolute value, you saw this graph. So let's not go into how to obtain this graph. But if you look at the graph, you can see that there's a sharp corner at x equals 0. All right, and here we cannot draw any tangent. So the tangent is undefined. All right. So and therefore you can see that since it's undefined, then we also have a local extremum. And for this case, from the graph, you can see this extremum is actually a minimum. So we have a local minimum at that point. Okay, let me now define this something very important called a critical number or critical point. Both means the same thing, and this is the value of x at which the function, at which the derivative of the function is 0 or undefined. Okay. So long as f prime equals 0 or f prime is undefined at this point x equals c, then we call this point x equals c a critical point or critical number. And of course, by that, it means if we have a local extremum, just remember, local extremum occur either when f prime equal to 0 or f prime is undefined. So that means so long as we have a local extremum, one of these happens. Either this happen or this happen. And therefore, the local extremum occur at a critical point or critical number. All right. So that's why in the last example, I think we can work out f prime, yeah, and equate to 0. And from that, we know we are going to get an extremum. So you can see that the local extremum always occur at a critical point. But the reverse is not true though, yeah? So take note of that. Local extremum occur at a critical point, but at a critical point, we may not necessarily have an extremum. I think I am going to show you one example in a short while to that effect. Okay, we have a polynomial in this example, actually a cubic expression, a degree 3 polynomial, and we want to find the critical numbers or critical points and also the local extremum or extrema. Okay, so to do that, of course, we work out the derivative and then we equate to 0 to find the critical number, right? The critical number. So this is what we do. So we differentiate this one, all right, and then you can factorize. After you differentiate, you can factorize. Now, if you equate this to 0, equate f prime to 0, you will find there are two critical points or critical numbers that occur when x equal to 2 and minus 1. So minus 1 and 2 will make f prime equal to 0. So we call these 2 critical points or critical numbers, all right? And of course, the critical number will correspond to the local extrema. And if you look at the graph of this cubic equation, it go like that. You can see that at these 2 points, the tangent is horizontal. And by definition, we call these critical numbers or critical points at minus 1 and 2. So it's just like that, very simple concept. So this example shows you a case when the derivative is actually undefined, and that will also correspond to critical point as well, right? So this is a function. This is a function. So to find the critical point, we always work out f prime, yeah, the derivative. So differentiate this. I think you know how to differentiate, right? Of course, you need to apply what you call chain rule to differentiate this, all right? So using the chain rule, you differentiate, you obtain this expression, and you can see that this derivative can never be 0, isn't it? No matter what x is. First of all, if you look at this function, right? This function, you know the domain. The domain can be from minus infinity to infinity, because the x can take any value between minus infinity to infinity, all right? So that is the domain of this function. So within the entire domain, that is the entire x-axis, all right? No matter what happened to x, then f prime can never be 0. Okay, so there isn't any horizontal tangent at any point, all right? But if you look at the denominator, we have a 3x plus 1 to the power 1/3, and that can become 0 when x equal to minus 1/3, right? So if x is minus 1/3, you have 2 divided by 0, which is undefined. Therefore, at x equal to minus 1/3, the f prime is undefined, right? So this should be a prime here, so the prime is missing actually. Let's insert it back. There should be a prime here. So at x equal to minus 1/3, you have 2 divided by 0, so f prime become undefined. And but this 1/3, this minus 1/3, of course, is within the domain because the domain is the entire x-axis, right? Therefore, for this function, there is only one critical number at x equal to minus 1/3. So that's the critical number, all right? And that from the diagram, you can see this corresponds to a local minimum. And of course, this is also a absolute minimum because this is the smallest within the entire domain, all right? So it is both local and absolute for this case. And of course, you know, from the diagram, we determine whether it's a minimum or maximum. But in fact, mathematically, we can do that also, which I will show you how in a short while. Now, this example shows you the critical point. Now, just bear in mind, I was saying that extremum always occur at critical point. But when you have critical point, doesn't necessarily imply that there must be a extrema. And this example shows one of such cases, right? So let's consider this function, x cubed, all right? So this is a function. So to find a critical point, you always differentiate it and equate to 0 to find the value of x. Either equate to 0 or find the value of x for which f prime is undefined. So either way will give you what we define to be the critical point or critical number. So to find a critical number, we always differentiate, all right? So x cubed differentiate, you get 3x squared. 3x squared cannot be undefined, right? Cannot be undefined. So we look for 0. We look for the value of x for which this f prime becomes 0. So equate fx to 0, you can solve this one, 3x squared equals 0, give you x equals 0. So this is the only critical point, all right? So only one critical point at which the tangent is horizontal because f prime equals 0 at that point, right? So if you look at the diagram, x cubed go like that is kind of S shape, right? Maybe inverted or a mirror image of an S. Okay, so if you look at this point x equals 0 right at the origin, we can draw a tangent at that point, and the tangent is actually the x-axis, horizontal, right? Because f prime equals 0 at that point. So you draw a tangent at that point, it's actually the x-axis. But does this correspond to an extremum? No. It cannot be maximum, it cannot be minimum, right? Although f prime equals 0, okay? So just bear in mind, just repeat one more time. Extremum always occur at critical point, right? Critical point is where f prime is either 0 or undefined, right? So we call this critical point. So extremum always occur at critical point, but when you have critical point, it does not necessarily mean that you have extremum. Like this case, definitely this is a critical point because f prime equals 0. The tangent is horizontal, so this is a critical point, okay? But it is not maximum, it is not minimum. In fact, this point, we call it the point of inflection. I'm not too sure whether it's the next slide, maybe maybe a few more slides, I don't know. Now another example, this one. This one is the inverse of x cubed. So x to the power 1/3. Okay? I hope you still remember inverse function. So you see, it's just you draw a line x equal y, they are mirror image about the line y equal to x. So this is y equal fx equal to x1 to the power 1/3, and to find a critical number, then we differentiate. Yeah, we always differentiate to find critical numbers or critical points. So when you differentiate x to the power 1/3, you get this. All right, and you can see that this is This is 1/3 times 1 over x to the power 2/3, right? Because it's minus. Minus is reciprocal. So you can look at it when x equal to 0, what happened? You have 1 over 0, isn't it? So therefore, at x equal to 0, f prime is undefined. And we still call this critical number. Remember, critical number is where f prime is either 0 or undefined. So this f prime is undefined at x equals 0, so therefore it is a critical point. So critical point occur at x equals 0. But if you look at the diagram, look at the curve, it goes something like that. All right, it's a mirror image about y equals x for x cubed because they are inverse to each other. You look at it, definitely this point at x equals 0, at this point, it cannot be an extremum, isn't it? Therefore, this function doesn't have a local extremum at this critical point. Yeah? There isn't any local extremum there. All right? Okay, so I hope you can now remember. So when you have critical point, doesn't mean that you must have an extremum. But extremum always occur at critical point. Critical point is where the f prime is either 0 or undefined. So these are the few facts, right? So another example, 2x squared over x plus 2. Now take note, this one is not part of the question, just a caution. If you look at this function, the domain can be anything other than -2. Why? Because you put x equal to -2, the function is undefined. So at x equal to -2, it cannot be the domain, right? So the domain is anything from -infinity to infinity except -2. So this point is out. It's not in the domain of this function, all right? Okay, so what is the significance of that? Let me explain here. Okay, so this is a function we have. We want to find the critical number. Same thing, right? What do? Whenever you find critical number, you always differentiate and see whether you can find some value of x for which the derivative is 0 or undefined. So we differentiate. So to differentiate this, of course, we use quotient rule. We apply quotient rule, and everyone should know how to apply quotient rule now. And then simplify this, we get this thing here. All right? So what are we looking for? For critical point? Critical point occur where f prime is either 0 or undefined. We must find all the value of x at which f is 0 or undefined. So you look at f prime here. You can see that f prime is 0 when x equals 0, right? Because of the numerator, you have x there, right? So when x equals 0, f prime equals 0. Not only that, when x equals -4, f prime also 0. So 0 and -4, right? 0 and -4 are two critical points. What about the case when f prime is undefined? Well, if you look at the denominator, when x equals to -2, then you have something over 0. And then f prime is undefined at x equals to -2. Remember, critical point, at critical point, f prime is either 0 or undefined. So does it mean that x equals to -2 is also one of the critical points? Because over there, f prime is undefined. For this case, the answer is no. Although f prime is undefined at x equals -2, but this x equals -2 is not within the domain. It doesn't count. It's outside the domain. You look at the domain of the function f I explained earlier. X equals -2 is not in the domain. All right? In other words, x cannot be equal to -2. Yeah? So therefore, for this case, there are only two critical points at 0 and -4. All right? Okay. So this theorem perhaps explains how we can work out absolute maximum or absolute minimum. Okay. So what it says is that if you have a closed interval, then the absolute extremum can be maximum or minimum. Must occur either at the critical point. You know that, all right? You know, just now I was saying that the local extremum occur at critical point. And local can also be absolute. You have seen a number of scenarios I showed you earlier, a lot of curves, right? So local extremum can also be absolute, right? You saw that, right? Therefore, if you look at the critical point, you have either a local maximum or local minimum, which can also be absolute. Therefore, the absolute extremum occur at critical point. Not only that, because this is closed interval, the two endpoints are included in the interval, and therefore, at the critical point, it may not be the absolute extremum. Definitely, it's a local extremum, right? But it may not be the absolute, because at the two ends, since it's closed interval, at the two ends, the functional value can be the absolute extremum. If you look at this diagram, this curve something like that. If you look at, let's say, this point, well, this point is a critical point, right? You know that because the tangent line is horizontal, so we have critical point. So this one is a local maximum. but definitely it's not the absolute, because there are many, where at this point, right? There are many points, where are we now? There are many points somewhere on the curve, this part of the curve. Any point on this part of the curve, the value is higher than this value. So this is a local. While this is a local maximum, it cannot be absolute, right? This point also, this point is a local minimum. You know that, right? But it's not the absolute, because this part of the curve, any point on this part of the curve, the value is below this value. Okay? So, therefore, this can be local, but it cannot be absolute. This point is the absolute as well as local. Okay, this one is local because f prime equals 0, right? F prime equals 0 give you the local extremum. But this is also absolute because it's the largest within the whole domain, right? And at one end, the other end, we have an absolute minimum. So what this theorem says, it will provide you, actually, as I said earlier, it will provide you a way to determine absolute extremum. We have example later on. We have a lot of examples, okay? I will refer you to this theorem when we come to that. So if you want to find the absolute, not too sure whether the next slide will explain that. Yeah, okay. Now this theorem will give you a simple way of determining the absolute extrema, whether maximum or minimum. So what you need to do is find all critical points, right? So you have a function. You find all the critical points, all right? And then find all the functional value at all the critical points. For example, if you have this one, you're going to find all the critical points. So at this point, tangent horizontal, we call critical point, right? Critical point. Find out all the functional value at these 3 points. Okay? And then what to do? Then we also find the functional value at the end points, right? So that means this point, you must find the functional value, this point also, because the 2 ends are included, and then do a comparison. So you have one value here, compute the functional value here at the 3 critical points, and also at the 2 endpoints. You have 5 values, and then compare. The largest one, amount of 5, for this case, we only have 5 points. So the largest amount of 5 values is the absolute maximum. The smallest among all the 5 values is the absolute minimum. It's as simple as that, yeah? So this is how you determine absolute maximum or minimum. All right? Find the values at the critical point as well as the 2 endpoints, and do a comparison. Okay, let's look at this example, how we can do so. All right, so we still have the same polynomial, actually. This is a cubic function. And the interval we are considering, however, the interval we're considering is the closed interval from -2 to 4. Okay, closed interval. All right? And this function is the same function as in the last example, previous example, 3.6, same function. Okay? And over there, we already obtained the critical point in example 3.6. You just differentiate and equate to 0. So we obtain the 2 critical points at -1 and 2. This one has been worked out for you in the previous example. Okay, so of course both are within this interval. Now we only consider this closed interval, right? These 2 endpoints, these 2 critical points, -1 and 2, it happened that both are within the interval, so we have to consider both because they are within the interval. Okay, so what we do according to this theorem, we need to find the functional value at the critical point, and the 2 critical points are -1 and 2, so let's substitute into the function. Yeah, substitute x equals -1 and 2, and the functional value turned out to be 12 and -15, respectively. Not only that, we must also find the value at the endpoints, because the endpoint can be the absolute extremum, right? So the 2 endpoints are at -2 and 4, right? Look at the closed interval. So we use x equals -2 and also x equals 4, put them inside the function, and we can work out the two functional value at the two endpoints turn out to be 1 and 37. Okay? Just substitute x equal minus 2, you get the functional value 1. 4, you get 37. So you have 4 values, right? At the two critical points right here, and also at the two ends. Minus 2 as well as 4. 4 value, all these 4. And then we just compare. The largest, of course, is this one. So at x equal 4, we have the largest functional value. So this is the absolute maximum. Okay? We don't have to look at the graph already, right? Based on the function, we can work out the critical point and also the functional value there, as well as the functional value at the two endpoints. So we have 4 values, and then we just compare. We don't have to look at the graph. We can say this point, 37, occurring at x equal 4 is the absolute maximum. And the minimum value is this one, minus 15. So this is the absolute minimum, occurring at x equal to 2, all right, at the critical point. So this one is at the critical point, but the maximum occur at x equal to 4, as you can see from the diagram. But of course, without the diagram, we also know that this corresponds to x equal to 4. That gives you the absolute maximum, and that is at the end point. Okay, so after that, then I think let's go a little bit deeper than that. So let me define what we mean by increasing function and decreasing function. I think if you look at the diagram, it's very simple. You look at the word, I mean, you can digest the word. So long as it goes like that, increasing, right? X, fx. So this one increasing. Well, it can be like that, also increasing, right? Yeah? So these are increasing function. So as you move along the x direction, the value of the function goes up. So we call this increasing function. On the other hand, decreasing like that, decreasing. It can be like that, right? So this one is decreasing. This one is increasing. Okay? Increasing and decreasing function. Now, why we need to know that? Well, from there you can see from this graph, okay, this function can be increasing and decreasing depending on which portion we are referring to. So if you look at this part, obviously the function is increasing, right? Followed by decreasing, and then increase, decrease. So it depends on which part we are looking at, all right? But you can see that whenever the function is increasing, then the tangent, if you draw a tangent on that part for which the function is increasing, then the tangent definitely have a positive slope. If you look at this diagram, increasing, right? So you draw a tangent line anywhere, so you see the two tangent lines, the two straight lines, the slope is positive. On the other hand, when you have decreasing function, you draw a tangent line to at any point, the slope is actually negative. Therefore, just by look at whether f prime is positive, f prime denotes the slope of the tangent line, right? So whatever function given to you, differentiate and see whether it's positive or negative. Positive f prime meaning that the function f is increasing. So f increasing, the tangent line have positive slope. So f prime is positive when the function is increasing. On the other hand, when the function is decreasing, you draw a tangent line, of course, the slope will be negative. So telling you that f prime is negative. So f prime positive, increasing. Decreasing, f prime negative. You can see, right? You draw any tangent, isn't the slope of the tangent negative, right? Increasing function, f prime big positive. Decreasing, negative. So we can look at the value, the sign of f prime, whether it's positive or negative, to tell whether the function is increasing or decreasing. Okay? This is actually the theorem. All right? So long as f prime is positive, then the function is increasing. like what I write down here. Yeah? F prime positive, increasing. F prime negative, decreasing. So this is the theorem 4.1. Now, what is the significance of that? Why do we need to bother about whether the function is increasing or decreasing? Well, because of that, we can make use of this to determine whether an extremum is maximum or minimum. Yeah? If you look at this diagram, obviously we have a local maximum on the top there, local maximum. You can see that the function must go up and come down. Therefore, if the function changes from an increasing part to a decreasing part, then you know that you have a local maximum. Okay? Just look at the critical point is not good enough. We know that at critical point, we know that the extremum occur at critical point. But we do not know whether it is a maximum or minimum. And this provides you with a simple check or whether, you know, the extremum corresponds to maximum or minimum, depending on whether the function starts with an increasing and then followed by decreasing, or the other way around. If it is the other way around, obviously you have a local minimum. Yeah? Okay. So this will give you, based on this concept, we have a simple test to confirm whether a local extremum is maximum or minimum. Depending on whether f changes from increasing function to decreasing, in that case maximum, or decreasing and then followed by increasing. All right? And of course, if f prime doesn't change sign, right? Let's say from increasing to decreasing, f prime, of course, will change sign from positive to negative or negative to positive. It depends on which way it goes. From positive, negative, that means from increasing to decreasing, you have a local maximum. Right? If it is from decreasing, from f prime negative to positive, then you have a function start with a decreasing part, followed by increasing. You have a local minimum. All right? So this is what the first derivative test is. What if f prime equal to 0 then? What if f prime doesn't change sign? So if f prime all the way is positive or all the way is negative, then in that case, we don't have a local extremum. All right? That corresponds to case 3 here. All right? Okay, so with that, I think we can work out more details about this local extremum. All right, so what we want to do is to find the local extrema for this function. All right, so obviously we have to find the critical numbers, right? Because local extremum always occur at critical point. So to get the critical point, we work out f prime, like all the previous example we went through. So work out f prime, you just differentiate this quite easily, right? Differentiate them, you get the two terms, and then combine them, you get something like that. So this is f prime, okay? And from that, we can observe there are two critical points. First one, when x equal to 6 upon 5, this will give you 0 slope. So that means at x equal to 6 upon 5, then the tangent is horizontal, isn't it? Because f prime equals 0. On the other hand, when x equal to 0, then you would have a non-zero number divided by a 0 number for f prime, which makes it undefined. So remember, critical point is where f prime is either 0 or undefined. And therefore, we have two critical points. 6 upon 5, one of them, and also 0. Okay? All right, so we have two critical points. One corresponds to a horizontal tangent. The other one corresponds to an undefined first derivative. When f prime is undefined, what does it mean? It means we have a sharp corner, isn't it? Remember, if you have a sharp corner along a curve, then you cannot have a tangent. You cannot draw a tangent to at a sharp corner, isn't it? So at this point, x equals 0, we expect the curve to have a sharp corner. Whereas at this point, f prime equals 0, So that is where the tangent is horizontal, isn't it? Okay, but our aim is to find the local extremum. Now we are going to use this so-called first derivative test. What is it? Well, it depends on whether f prime changes from positive to negative or negative to positive. Then we can determine whether it's a maxima or minimum. All right? So what we're going to do now is to work out we are going to work out whether this f prime, which way does it go? Is it changing from positive to negative or the other way around, or what happened to f prime at different value of x, all right? So since this one has got a numerator, denominator, what we are going to do is to examine the sign of f prime. We are worrying about a sign. The sign will indicate whether the function is increasing or decreasing, isn't it? So let's check the sign of this function by look at the numerator and denominator separately first along a number line. So if you look at the numerator, 5x minus 6, so this one will change sign. It depends on the value of x, okay? Anything less than 6 upon 5, then you substitute into this numerator, you get negative value. And if anything bigger than 6 upon 5 for x, then the numerator, this thing, will be positive, all right? And of course, right there, at x equal to 6 upon 5, you substitute inside, this value is 0. So this is why, therefore, we have a 0 here at that point, right? On the left side, this is negative. On the right side is positive. So that's the numerator. Now let's look at the denominator. 3x to the power 1/3, this one, okay? So if x is positive, then you take a positive number to the power 1/3, what do you get? It is always positive, isn't it? Let's say 8 to the power 1/3 is positive 2, isn't it? So if x is positive, the 1/3 power will also be positive. So 0, right? So 0 is this point. So on the right-hand side, when x is bigger than 0, then the cube root is positive, so positive. On the other hand, when x is negative on this side, right, this part, when x is negative, a negative number to the power 1/3 is always negative, isn't it? For example, minus 8 to the power 1/3 is minus 2. Because minus 2 times minus 2 times minus 2 will give you minus 8. All right? So when x is negative, so this one, the cube root is negative. So we have this thing. Negative on this side, positive when x is positive. All right? So what we want is f prime, right? So f prime is the numerator divided by the denominator, right? So let's look at it. So if the x value is bigger than 6 upon 5, then the numerator positive, denominator also positive, this part also positive. So positive divided by positive, you get positive. Okay? Now, in between 0 and 6 upon 5, right, within this range, between 0 and 6 upon 5, the numerator is negative, denominator is still positive. So you divide them, you get negative. So we get negative value. So we get negative value here, right? Between 0 and 6 upon 5. Okay? Now, when x is less than 0, then the numerator is always negative, but the denominator is also negative when x is less than 0. So when you divide them, negative divided by negative, you get positive. So for this range of x value, f prime is positive. So we determine the sign, right? So what happened? For this part, when f prime is positive, increasing, right? The function is increasing when f prime is positive. Therefore, the pink arrow pointing upward denote that the function is actually increasing for this part, because f prime is positive. For this part between 0 and 6 upon 5, the f prime is negative. Negative here, you can see negative corresponds to a decreasing function. So function is decreasing. That's why there is a arrow pointing downward. denoting denoting the function is decreasing, right? For the other part, this one, the f prime is positive, so the function increases. So you can see the function actually goes up, come down, and goes up. It behaves this way. Therefore, you can see that we have a local maximum at this point, x equals 0, and a local minimum at that point, right? Local maximum occur at x equals 0 because this thing go up and down. The function f go up and down, right? And then at x equals 6/5, it changes from decreasing to increasing. Therefore, at x equals 6/5, this corresponds to a local minimum. So this one we are using what we call the first derivative test. Why call first derivative test? Because we are looking at the value of the first derivative, f prime. Based on f prime, the first derivative, we can determine whether the local extremum is a maximum or minimum. Okay, maximum here, minimum here. So if you look at the graph of this function, it confirms what we conclude from this first derivative test. You see there is a local maximum here and a local minimum here, right? That agree with the first derivative test. So now with the first derivative test, we don't have to rely on the graph already. Just carry out the first derivative test. At least we can tell, where we have local maximum and local minimum. All right. And of course, this point, the f prime is undefined, right? I mean, we worked out just now. Undefined f prime is undefined at x equals 0, so that corresponds to a corner, isn't it? So we can see there is a corner here. We can't draw any tangent. There isn't any tangent at this point. Okay. On the other hand, at the other critical point, at this point, then the tangent is horizontal. F prime equals 0 there. Okay, another example. We want to find the local and extrema approximately. Why approximately? Well, because we can't find the exact value. Sometimes we can't find the exact value. Okay, this is a fourth degree polynomial. All right, we want to determine the local extrema. And of course, we have the first derivative test. So we can do better than that. Not only we can determine whether we have local extrema, but we can also classify it into whether it is a maxima or minima. Yeah. Just use the first derivative test. Okay. So of course we got to find a critical point or critical numbers. To do that, we differentiate, right? Find critical number, you always differentiate. So take the function, differentiate once, you get the first derivative. So it's this one, okay? Now, what we want to do is to find the critical point at which f prime is 0. Therefore, if you equate f prime to 0, then you are going to solve this equation, something like that equal to 0. How do we solve for x value? This cannot be factorized, okay? Cannot be factorized. That is the reason why we can only find it approximately. Well, we can do a very accurate approximation, but still an approximation, all right? Okay, how do we solve these equations? 4x cubed plus 12x squared and so on equal to 0. We can't factorize, then what to do? Remember, I show you this, one of the application of this differentiation called the Newton-Raphson method or Newton's method. Remember the Newton method? Right? Newton method is to solve an equation for the 0 when we cannot do it analytically. Yeah? So using a root finding method such as the Newton method, which I took you through maybe last week, then we can solve this equation to obtain 3 zeros. Turn out to be at the point A, B, and C approximately to be a minus 2.96, something like that, all right? So these are the 3 locations at which f prime equals 0. So these are called the critical points, right? Because f prime equals 0 at these 3 values of x And if you look at the diagram for f prime here, then this corresponds to point A, point B, point C here. When f prime equals 0, it happened over there at these three locations. And this value will obtain numerically, or using the Newton method, or maybe some other method which is not covered in this course. Okay, anyway, we obtained the three critical points. Then how do we know whether it's a maximum or minima? Well, we can work out the sign of f prime, right? If f prime positive, increasing, f prime negative, decreasing, something that you should bear in mind. So, these are the 3 points A, B, C, at which f prime equals 0. So, at these 3 points, we have either local maximum or local minimum. So, whether we have local maximum or minimum, it will depend on whether the functions start from decreasing and then increasing, or the other way around. So, what we're going to do is we know the value of A, B, C, right? A is minus 2.9 something. So, just substitute some value. Try some value. Maybe, for instance, try something just slightly less than minus 2.96. Maybe try minus 3, let's say. Try x equal to minus 3, slightly less than A. So that means somewhere here, right? Then you can find f prime, because we know f prime, right? Substitute the x equals 3, you get f prime. So you can see that you get a negative value. You do the calculation, yeah? You get a negative value. Therefore, on this side, f prime is less than 0. And then when it is bigger than A, then maybe minus 2.5. You can take x equal to minus 2.5, which is bigger than this value, and do the same thing, substitute into f prime. Then you can determine the sign of f prime, which work out to be positive number, positive. So, around this point, x equal to A, the function changes from a decreasing one to an increasing one. Obviously, this corresponds to a local minimum. And you can do the same thing to the other 2 points, right? So at point B, use some value just slightly less than B and evaluate the sign of f prime at that point, just like point A. So get the f prime at some value slightly less and slightly more than the value at x equal to B. Then you will see that it starts from an increasing function to become a decreasing function, telling you that there is a maximum. So this is the first derivative test, right? We see whether it's changing from positive or negative to positive. One can determine whether it's a maximum or minimum. So I think you just do the rest. For point C, you just do the same thing. Then you know that you know whether you have maximum or minimum. All right? Okay, now when we talk about increasing and decreasing function, increasing function can be like that, So they can be increased in different manner. Although either case, the slope of the tangent is always positive. F prime is always positive for increasing function. But the increasing function can increase in a different manner. So this one go up like this. Okay, this one go up like this. For this case, if the function go up like this, it's just like the left side, the diagram on the left side. So this is what we call a concave upward, because it's going upward, concave upward, right? On the other hand, the other one, yeah, the function is increasing, but it's turning down, right? The direction is turning down, right? So this one we call concave downward. So this is a concavity, whether it's concave upward or concave downward. So upward is like this for increasing function, yeah? Downward for increasing function, like this. So for increasing function, the concavity can be either way, can be up or down. We can have increased function also, isn't it? Okay. Now, if you look at the slope, now of course we have to find a way of determining the concavity, whether it's concave up or concave down. So how do we determine? All right. Then if you draw the slope, if for increasing function it go up like this, let's say go up like this. obviously the tangent are always have positive slope, isn't it? You can see the 3 pink line, they all have positive slope. But the difference is that for a function which is concave upward, then the slope of the tangent line also increasing, isn't it? Because this one is not so steep, right? This one not so steep. But if you look at the a larger value of x, then the slope of the tangent become larger. And then if you move further along the x-axis, you see the third one, this one, the pink line, the slope is very steep. So when it is concave upward, one can see that f prime goes up. F prime increases when it is concave upward. If f prime goes up, it means that f double prime is positive. Why? I think it's quite simple. The reason is quite simple. If you, okay, this is fx, right? So if you look at f prime, you see f prime for this case, so the slope is quite small, although positive. It starts from a small value, right? And then at this point, the slope is steeper, so the larger, so a point is higher. This one even higher. So you can see here, f prime behave like that. So if you differentiate one more time, that means you're looking at the tangent to f prime. The tangent to f prime will give you f double prime because it's just a differentiation of f prime one more time. So you can see the slope for this part is always positive, right? Okay? So when f prime goes up, it means f double prime is positive. I mean, it's just like increasing function, right? When the function increasing, right? When f goes up, increasing, then f prime positive, right? For the same reason. So when f prime goes up, it means f double prime is positive, just like the increasing function, isn't it? On the other hand, when the curve is concave downward, then you can see from the diagram comparing the slope of the 3 pink tangents, then you see that f double prime is negative, okay, for increasing function. What about when the function is decreasing? Okay, when the function is decreasing, it can decrease in different manner also. It can decrease in this way, which is concave upward, because it's like there's a tendency that it go up, right? Now, if it decreases this way, it's called concave down. All right? So if you look at this case, when this is concave upward, same thing, f prime goes up, and therefore f double prime is positive. You can see f prime goes up because this one is large in the negative manner. And this one also negative, but not so big already. So this one, let's say this one is minus 10, the slope, this one, minus 10, and this one become maybe minus 7. So the slope goes up, right? F prime goes up. And come to this point, the slope will be much more level. So f prime may be minus 3, minus 10, minus 7, minus 3. So the f prime actually goes up, right? So when f prime goes up, it also means f double prime is positive. On the other hand, concave downward will give you something like that. So how do we tell? So if you concave up, second derivative positive. Concave down, second derivative negative. Concave up, second derivative positive. Concave down also. Therefore, concave up means f double prime positive. Okay? Let's write down the major thing here. Concave down means f double prime is negative, regardless of whether the function is increasing or decreasing. You can see that, right? For increasing function, yeah, up means second derivative positive. Decreasing function also, up means the second derivative is positive. So there's no difference whether the function is decreasing or increasing. So long as f double prime is positive, it means the function is concave up. If it is negative, for the second order derivative, it's concave down. Okay? So I think from the diagram we can see that. So concavity for decreasing function, right? So it's either positive or negative depending on whether it's concave up or concave down. Okay, this will summarize our major conclusion from this concept. All right? So concave up, when f prime always increasing. Okay? And therefore, f double prime is positive. Concave down, f double prime negative. All right? For both increasing or decreasing function, there's no difference between them. So long as f double prime bigger than 0, it doesn't matter whether the function is increasing or decreasing. Concavity is always up, and vice versa, like that. All right? So we can use f double prime to determine the concavity, whether it's up or down. All right? But take note, we can't use it to tell whether the function is increasing or decreasing. To tell whether the function is increasing or decreasing, we have to use f prime. F prime positive, function increasing. F double prime positive, function is concave up. It can be increasing, it can be decreasing. We don't know, based on f double prime. All right? Okay, so if you want to determine whether the function is increasing or decreasing, use what I put down there. Positive, use the first derivative. Yeah? Second derivative, you can determine concavity. First derivative, you can determine whether the function is increasing or decreasing. All right, so in this case, how do we determine the concavity? Concavity, remember, concavity, we always use f double prime, the second derivative. So this is the application of differentiation, isn't it? Yeah? So take this function, a cubic, all right? So we want to determine where the function concave up and concave down, all right? So that means, okay, to check the concavity, we work on the value of f double prime. Not the value, the sign of f double prime, whether it's positive or negative. The value is not important, yeah? So long as it's positive, it means concave up, negative, concave down. So differentiate this twice, all of you know how to do it. Differentiate once, and then differentiate one more time, you end up with f double prime equal to 12x plus 18. And that could be positive or negative, depending on the x value. So if x is bigger than minus 3/2, then you have a positive value for f double prime, telling you for this part, when x is bigger than minus 3/2, it's concave up. On the other hand, when x is less than that, then the sign changes, become negative. Yeah? F double prime become negative. And this negative means concave down. Concave down, all right? Okay, now since we want to draw a graph, concave up or concave down, we don't know whether the function is increasing or not, isn't it? Right? So we have to work on f prime to determine whether the function is increasing or decreasing. So work out f prime. F prime is the first derivative. So this one, when you differentiate once, you get that, and then you can arrange it to this form. All right? So how do we determine whether the function is increasing or decreasing? We have an early example. So if you look at that, f prime is 6 times x minus 1, x plus 4, right? So we just look at the sign of f, the sign of the different factors in this expression to determine the sign of f prime. So what do? Okay, so one of the factor is 6 times x minus 1. Okay, so this one obviously is positive. When x is bigger than 1, it's positive. When x is less than 1, x equal to 1 is right here. So on this side, x is less than 1, therefore negative. Okay, right at this point, the value is 0. When x equal to 1 is 0. And then the other factor is x plus 4, right? X plus 4, this one, okay? So x plus 4, same thing. So long as x is bigger than minus 4, then this is positive. If x is less than minus 4, then this becomes negative. So like that. And the function is this, right? 6 times x plus minus 1, x plus 4. And therefore, we multiply the first two number lines. These two lines multiply together. So when x is bigger than 1, we have a positive times a positive, therefore we get positive. When x is between minus 4 and 1, this part is negative. This is still positive. Therefore, multiply the two, minus, plus, you get minus, right? Minus here. For this side, x less than minus 4, this is still negative, but this now is now negative. So negative times negative, you get positive. Okay? So this positive, negative, positive will tell you what is happening to f prime. And you all know that when f prime is positive, function increasing. Yeah? F prime positive, increasing function. So we use the pink arrow, goes up, and negative slope means coming down, and positive slope goes up. Okay, so like that. So we know which part f is increasing or decreasing. Now, and of course, we know these 2 points, x equal to 1 and 4, 1 and minus 4, these are the 2 critical points because f prime equal to 0, right? When x equal to 1 and minus 4. So we can work out the functional value at these 2 points, okay? So f equal to minus 4, we get 102, substitute into the function, yeah? This function. Okay? And then f1, substitute into the same function, you get minus 2/3. This f minus 3 upon 2 is because we can see the concavity changes sign at x equal to minus 3 upon 2. The concavity changed from concave up to concave down to concave up, right? When x is less than minus 3 upon 2, concave down. Bigger than minus 3 upon 2, concave up. So concavity is changing from down to up at the point x equal to minus 3 upon 2. So at x equal to 3 upon 2, we can work out a functional value. At minus 3 upon 2, substitute into the function fx, we get a value 79/2. Now with all this information, now we can sketch a much better graph. What do we know? Well, we know the change in concavity. We know which part the function increasing, which part the function is decreasing, right? We also know the value of the function at this point minus 3 upon 2, at which the second derivative is 0. Okay? So with this information, this summarizes the information we obtained. We can now do a very good sketch of the function already. Okay, when x is less than minus 3 upon 2, 3 upon 2 is here, right? Minus 3 upon 2 is here, sorry. This part, this corresponds to minus 3 upon 2, right? So when x is less than minus 3 upon 2, it concave down, so this part. When x is bigger than minus 3 upon 2, concave up, so this part, like that, right? Okay? And of course, not only that, we also know that when x is less than minus 4, the function is increasing. So this part, confirm this part go up. And then when x is bigger than 1, also the same thing. For this part, this is x equal 1. X equal 1. Right? So when x is bigger than 1, we know that the function is increasing by look at the sign of f prime. F prime is positive for that part. Okay, so, and also, if you look at this point, minus 3 upon 2, when x is less than that is concave down, and then from concave down at this point, when x crosses this point minus 3 upon 2, concavity changes from concave down to concave up. So the concavity is changing at the point minus 3 upon 2, right? The concavity changed from concave down to concave up at the point x equal to minus 3 upon 2, isn't it? We have worked out the concavity using f double prime. And this point is called point of inflection. When there is a change of concavity, change from up to down or down to up, we call this point of inflection, just like the S shape or the x cube. The graph for x cube is also exhibit this so-called point of inflection because it's an S-shaped thing. So you draw the letter S, you follow the letter S. The concavity does change from concave up to concave down. So in the middle of the letter S, there's a change of concavity. At that point, we call this the point of inflection. All right? So the point of inflection is where concavity is changing. So long as we know the concavity is changing, then we can determine the point of inflection. Okay? All right, I think this will define what I mentioned just now. So long as there is a change in concavity from up to down or down to up, take out this one, it's not supposed to be there. From up to down or vice versa. That means the reverse. From down to up also. Okay? So I think cross out that, but this word is not there. So when there's a change of concavity, we say that we have a point of inflection. For example, just now, at minus 3 upon 2, then we have a point of inflection. All right? And also at a point of inflection, f double prime equals 0. Why? If you look at the change in concavity, concave up, f double prime positive, concave down, f double prime negative. So when f double prime equals 0, that is where the concavity is changing from up to down or down to up, isn't it? So at point of inflection, where concavity is changing, definitely f double prime equals 0. But the reverse is not true. If f double prime equals 0, doesn't mean that we definitely have inflection point. Maybe we have, maybe we don't have. Okay? So inflection point always correspond to f double prime equals 0. But f double prime equals 0 doesn't necessarily mean we have inflection point. All right? Only one way. Inflection point happen at f double prime equals 0. F double prime equals 0 doesn't mean we have inflection point. Maybe we have, maybe we don't. Okay? I think in a later example, it will show this case when f double prime equals 0 doesn't correspond to inflection point. You just have to remember the definition of inflection point is where concavity is changes sign. Concavity is changing from up or to down or down to up. Then we say we have a point of inflection. All right? Okay, here we are going to determine the concavity and also to locate the point of inflection if there are any. All right? So this is a polynomial, 4-degree polynomial. So to check the concavity, we need to work out f double prime. All right? And of course, to determine whether the function increasing or decreasing, we base on f prime. So I think it's summarized here. So you want to tell whether the function increasing or decreasing, use f prime. Concavity, use f double prime. First of all, we check whether the function increases or decreases, all right? So using f prime, of course. So differentiate these ones. Differentiate these ones. You get something like that, and we can solve this, or we can factorize this x squared minus 3 into these two factors. So to examine the sign of this f prime, because we want to confirm whether the function f is increasing or decreasing. So we work out the sign of f prime. Using the same method I showed you in a few earlier examples. Yeah? So just using the number line, based on the factor appearing in f prime, we have 3 of them, 4x, x minus root 3, x plus root 3. So based on this, we can draw 3 number lines, right? 4x, x minus root 3, x plus root 3, and then we can label the sign of these factors along the number lines. 4x, obviously, when x is positive, 4x is positive, right? So 0 is here, so this is positive x, you get positive 4x. Negative x, you get negative 4x. So straightforward. X minus root 3. So when x is bigger than root 3, so root 3 is here. So on the right side, x is bigger than root 3, and therefore positive. On the left side will be negative. I mean straightforward. We have done it a number of times already. So for the other factor, x plus root 3, so if x is bigger than minus root 3, this will be positive. So minus root 3 is here, so on the right side positive, on the left side is negative. Right here at this point, 0. Yeah? When x equals minus root 3, this factor is 0. So our f prime is the product of all 3, 4x times x minus root 3 times x plus root 3. So we multiply these 3 number lines together. Right? 4x multiply to this and multiply to this. All right. So for x bigger than 0, positive. For this one, positive. All 3 are positive. So you multiply all 3 factors, you still get positive. This part, between 0 and root 3, the first one positive, this part positive, this one negative, this one positive. So negative, positive, negative, positive, will give you negative. I multiply them. Okay? For this part, between minus root 3 and 0, so the first one is negative, second one also negative, third one positive. Multiply them, negative, negative, positive, give you positive. All right? For x below minus root 3, this part, the first one negative, second one negative, third one also negative. They're all negative. Multiply all 3 together, you get negative. So that tells you the function is decreasing for this part. Negative f prime means decreasing. So this one function increasing, this one decrease, increase. So this is the first derivative test. Okay, just look at f prime. We know the function behave like that. It comes down, go up, comes down, go up. At these 3 points, minus root 3, 0, minus root 3, 0, and root 3. We know how it behaves. All right? Now, of course, to check the concavity, we have to base on f double prime. Concavity, make use of f double prime to tell. Okay? So, differentiate one more time, we get f double prime 12x squared minus 12. And we can factorize it into like that, x minus 1 times x plus 1. Of course, we want to check the sign of f double prime so as to confirm the concavity, whether up or down, right? So, using number line again, so the first factor, 12 times x minus 1, anything bigger, when x is bigger than 1, positive, less than 1, negative. So we can draw that line. Right here at that point, the factor equals 0. When x equal to 1, this is 0, right? For the other factor, x plus 1, so long as x is bigger than minus 1, this part positive. This part negative, right? And right at this point, x equal minus 1, the factor is 0. Minus 1 plus 1, you get 0. So f double prime is the product of the two. So multiply the first 2 number lines. So this region, positive. This one is minus, plus. You multiply, you get minus. This one is minus, minus, multiply them, you get plus. So this plus, minus, plus is are the sign of f double prime at different range of x value. And based on that, we can tell the concavity. What happened? Positive f double prime means concave up. Negative means concave down. So this one is concave up, positive. Concave up always like that, right? Concave up, right? Okay? Concave down, negative. Concave down, right? Concave down. Okay? And then this part positive, f double prime positive, concave up. So this plane curve show the concavity. So this one concave up, yeah, positive, concave up, concave down, concave up. Go like that, you know, yeah. So what do we get from here? Now we can sketch the graph already, isn't it? Okay. So we know that and also if you look at it, it's changing concavity at -1 and 1, isn't it? Right? You see concave up, and then across this point, x equal -1, it changed to concave down. From concave down, at this point, x equal 1, it changed to concave up. So at 1 and -1, the concavity is changing. Therefore, we have two inflection points at which the concavity is changing. And these 2 points occurring at x equal -1 and 1. Concavity, when concavity is changing, we have inflection point. So at 1 and -1, so somewhere here. Inflection point, 1 and -1, right? This one is 1, this one is -1. So these are the two inflection points. And then on the left side, this side, below -1, less than -1, concave up, yeah? So this side, concave up, right? The function go like that, yeah? This side, yeah? Concave up. And then concave down, this part, concave down. And then concave up, yeah? So you can see that here. And of course, we know that the function goes down this way, go up, go down, go up, isn't it? So this one also tell you, go down, go up, go down, go up. So based on all this information, one can do a pretty good sketch of this function, like a W-shaped curve. Okay, let me see. Maybe just give me a minute just to finish this example before we take a break, all right? Because earlier on I was saying that at inflection point, f double prime always 0, right? But when f double prime equals 0, doesn't necessarily mean we have inflection point. So this example shows such case. Let's consider this function x to the power 4. All right? So we are doing the same thing. So let's look at whether the function is increasing or decreasing. So to do that, we work out f prime, right? F prime is 4x cubed. Differentiate one more time, you get 12x squared. So first derivative, second derivative. All right? From the first derivative, we know whether the function is increasing or decreasing. So from 4x cubed, when x is negative, 4x cubed will be negative, right? When x is negative, this is negative. Therefore, f prime is negative when x is less than 0. When f prime is negative, it means the function is decreasing. Yeah, look at here. Yeah, look at that one. Yeah. So when f prime is decreasing, when f prime is negative, this one negative, the function is decreasing. So when x is less than 0, the function is decreasing. When x is positive, 4x cubed, of course, is positive. So f prime positive, meaning that the function is increasing. All right? So if you look at the diagram, yes, when x is less than 0, function is decreasing. When x is bigger than 0, function is increasing. because f prime is positive, right? Now let's look at the concavity. We have to use f double prime to tell the concavity. So f double prime is 12x squared, x squared. So x squared is always positive, regardless of what x is. So this f double prime is always positive throughout the entire domain. So f double prime positive means the curve is concave upward. For all values of x is always concave upward. And if you look at the diagram, it shows that the whole curve is concave upward, right? Concave upward, okay? This is concave upward, right? Concave upward. So if it is concave upward, there isn't any change of concavity. Nothing like concave up to concave down or concave down to concave up. Concavity is always up, right? Therefore, there isn't any point of inflection. Now, if you look at f double prime at x equal to 0, f double prime also 0, right? And x equal to 0, f double prime equals 0. In this case, there isn't any change on concavity, and therefore, at this point, although f double prime equals 0, we don't have point of inflection. All right? So just bear in mind, at point of inflection, f double prime is always 0 because there is a change of concavity from up or down to up. So f double prime is 0 at the point of inflection. But when f double prime equals 0, doesn't necessarily mean we have point of inflection. And this example shows you the case. All right? So let's take a break. 50 minutes, yeah? 15 minutes break. Okay, so 3 minutes past 4 we start. Yeah? Yeah. Yeah. Okay. So I hope everyone is back. All right, so let's continue from here. At the critical point, and what we want to do is to discuss the concavity at the critical point, all right? So if the concavity is concave up or concave down at a critical point, then we know that we have a local minimum or maximum. I think a diagram will tell you this. So let's say if it is a critical point, and at the critical point, the f prime equals 0, so the tangent is horizontal. And if the range of x value, including this critical point, for which the concavity is concave up, then you know that you have a local minimum. On the other hand, of course, when it is concave down, then you have a local maximum. Okay. Now, to help you to memorize this thing, concave up, you have minimum, concave down, you have local maximum. You can think of a cup, you know, a U shape like a cup, you know. So let's say this is a cup shape, right? So cup shape, let's say you can, if it is in this position, you can put water inside, right? You can pour water inside a cup, you know, right? So if you pour water inside, then you have a local minimum. When you have poured, so f double prime bigger than 0, you can think of they can hold water, right? Positive. Positive, the cup can hold water, so minimum, right? I mean, it's just a way to memorize it, you know, yeah? On the other hand, if f double prime is negative, the cup cannot hold water, so the cup is upside down. Upside down, it will be in this shape, you have maximum. So it's just a way to memorize it. Okay, and then this will bring about the concept of the second derivative test, all right? So which says if we have, of course, we must have a continuous second derivative, all right? So within some interval. So if the second derivative is negative, like what you saw, that's what I mentioned just now, negative, meaning that the cup cannot hold water, then you have a local maximum at a critical point. On the other hand, when it's positive, then you have a local minimum. So and this is what we call second derivative test. So we have first derivative test and second derivative test, right? First derivative test, to determine whether minimum or maximum, what do? We want to see whether the function changed from decreasing to increasing. If the function changed from decreasing to increasing, then, of course, it corresponds to a local minimum, right? Decreasing to increasing. Decreasing to increasing, minimum. If the function changed from an increasing part to a decreasing part, you have a maximum. And how do we tell whether the function is decreasing or increasing? Using the first derivative. We call this the first derivative test, right? Right now, this will give you another test based on the second derivative, f double prime. We can also tell whether the extremum is maximum or minimum, simply using this second derivative test. All right. So let's try to make use of the second derivative test to do that. So this is a fourth degree polynomial. And of course, second derivative test, obviously, you need to work out the second derivative, right? So you need to differentiate this twice. So take that function, differentiate twice. First of all, differentiate once, it will allow you to determine the critical point, right? So by look at the f prime, you know that there are 3 critical points at 0 and plus minus 2, 3 of them, all right? But to determine whether it corresponds to maximum or minimum, then we have to look at the second derivative. So work out the second derivative, differentiate one more time, you get that, and then let's find at the critical point what is happening to f double prime. So substitute x equals 0, 2, and minus 2 inside. For 0, you get a negative f double prime. So according to second derivative test, maximum, all right? At the other critical point, at minus 2, then the value of f double prime is positive, so you get a minimum, local minimum. For this one, Similarly, you get a positive value and you get a local minimum. So if you look at the graph, the W-shaped graph, I think it's the same function we saw early before the break. So you can see we have a maximum at 0, but minimum at -2 and 2. So that is confirmed from the graph as well. Maximum here, local maximum, and local minimum at ±2. All right. So these are the use of second derivative test. Now, if the f double prime equal to 0, if you look at the second derivative test, f double prime less than 0, the cup can hold water, you have local minimum. Bigger than 0, the cup cannot hold water, the cup is upside down, you have a local maximum, right? Upside down. Yeah? What happens when f double prime equal to 0? Is it maximum or minimum? Then the second derivative is not able to tell you anything, right? Less than 0, definitely a local maximum. Bigger than 0, definitely a local minimum. What about equal to 0? So, we don't know, right? From the second derivative, we don't know, all right? Therefore, in this case, if you want to tell whether this corresponds to a maximum or minimum, you can't use the second derivative test. So you do something else. For example, you may go back to the first derivative test to determine whether the function is increasing, decreasing, or whatever happening, all right? So this is what happened, and I think we can have an example. Right, this example shows you this case when the second derivative test won't be able to tell you whether you have a local maximum or minimum. All right, so this is a function g, x plus 1 to the power 4, okay? So first of all, let's work out the critical point by look at g prime. So differentiate once, and okay, you get this, and of course you equate to 0. You equate to 0, that means the critical point is at x equal to -1, right? The first derivative, when you equate the first derivative to 0, you get a critical point. So x equal to -1 is the only critical point at which g prime, the first derivative, is 0. Okay? Now, if you look at the second derivative, differentiate this one more time, okay? And then at that critical point, substitute the value of -1 inside the second derivative. Using the second derivative test, this is what we do, right? So find the critical point, substitute the critical point into the second derivative. Positive means local minimum, negative means local maximum, but for this case, equal to 0. X equal to -1, g double prime equal to 0. All right? So we don't know. Second derivative cannot tell you. So we still have to rely on other way of finding or of determining whether we have minimum or maximum. So let's go back to the first derivative test. Don't think that, oh, since second derivative can do the job, let's forget about first derivative test. No, sometimes you can't. Sometimes second derivative doesn't work. This is the case, all right? All right, so when it is equal to 0, we can't use. So go back to the first derivative test. We want to check whether the function is decreasing, change from increasing, to decreasing, or vice versa. Okay, so when the critical point is -1, right? So if, let's say, you look at this function, g prime, to check whether the function is increasing or decreasing, you only consider the first derivative. That is why we call first derivative test. So from this g prime, we know the critical point is -1. So let's say on the left side of this critical point, when x is less than -1, maybe -2, or minus something that is more than 1, then you add 1, of course, this becomes negative. Negative to the power 3 is negative. So g prime is negative, right, when x is less than 1. Then what about x bigger than 1? Sorry, bigger than -1, because we are looking at the critical point. All right? So on the right side of the critical point, when x is bigger than -1, maybe 0.9 or something like that, then obviously this x plus 1 is going to be positive. Positive to the power 3 is still positive. So g prime is positive when x on the right side of the critical point. So you see, when x is positive, bigger than minus 1, g prime positive. Less than minus 1, g prime negative. So less than minus 1, g prime negative. Negative meaning the function is decreasing. So on the left side of the critical point, the function is decreasing, right? Look at this thing here, decreasing. On the right side of the point, the first derivative positive. Positive means increasing. So the function is changing from decreasing to increasing, obviously. At that point, this cannot be 0, right? At that point, the function changed from decreasing to increasing and therefore correspond to a local minimum. So something wrong with this one. It should be minus 1. This one should be minus 1. At the critical point, right? Let me change it. This is minus 1. Okay? At x equal minus 1, the critical point, we have a local minimum. Now, at this point, second derivative test doesn't work. First derivative test can tell you is a minimum. Second derivative cannot tell you. Okay? So, it depends on the situation. I mean, if g double prime is non-zero, yeah, you use the second derivative test. It definitely works. But it happens that if the second derivative is 0, then you have to go back to your first derivative test. So that means we cannot get away from it. You got to learn, you got to know both tests. If you think of, let's say I just learned second derivative test is good enough. No, that's not true. Sometimes second derivative test doesn't work. All right? Okay, if you look at the graph, it shows you like that, you know. So I mean, it's a U-shaped things like that. You clearly show there is a local minimum at minus 1 at x equal minus 1 here. Here, this one, yeah. Okay, and the second derivative is 0. Okay. All right, now this is what we can do to find the maximum and the minimum. And then the next application in differentiation is to do some optimization problem. Somehow this also related to maximum and minimum, right? Because when we want to optimize something, maybe we want to maximize a company's profit or something like that, then we got to optimize some variable, all right, some conditions. All right, so this is what we mean by optimization. So something is changing and we want to optimize a variable, all right? Now in optimization problem, I think there's some guideline here. First of all, if you can draw a picture is better than 1,000 words, right? So draw a picture, this will give you a better idea of what the problem is about. So if you can draw it, don't just, somehow imagine this is what it is, write it down and that will help you actually because we can look at it, and then you can insert more information on a piece of paper, much easier than what you can insert into your head, isn't it? Yeah? And then what we do is determine what variables and how they are related, all right? Because we want to optimize some variable, then we determine how they are related, okay? And then we see which variable we need to maximize or minimize, and then we just carry out the using whatever thing I just went through, maximum and minimum, to maximize a certain variable or minimize it. Yeah, I think all this will be shown in a few examples following this. All right. After that, then we can write an expression. We have to form an equation expressing link up all the variables, all right, and then determine which one we want to optimize or maximize or minimize. Then we just use whatever test we suitable, right? First derivative test, second derivative test, or whatever, to determine the maximum or minimum value, all right. And then, of course, this will lead you to the answer. I think this guideline, I think, is better illustrated by examples. So we are going to have a lot of examples here, quite a few examples, maybe 3 or 4. Okay, first one, we start with a simple one. Okay, we want to construct a garden of maximum area. So it's an optimization problem, all right? What happens is that we have some constraint. Optimization always subject to constraint. The constraint in this problem is that we have 40 meters of fencing, limited. This is the constraint we have. We can't have more than that, right? 40 meters of fencing. We want to use it to enclose a garden in this diagram, and we want to see what do we do to maximize the area of the garden under this constraint using a 40 meters of fencing. All right? We want to get the largest area. So it's an optimization problem. Okay? And of course, you can see that since we want to get the largest area, obviously we want to form an equation relating the area and the length of the fence, right? The length of the fence is 40. Okay? All right, so of course I draw a diagram. I mean, this diagram you don't need to draw, this one. This one is for pleasure viewing. So you need something simple. The simpler, the better, actually. Yeah, like this. Just a rectangle. I mean, the garden shape is a rectangular shape. By the way, we are not, another constraint is that the garden must be a rectangular one. We are not allowed to do any other shape, circular or whatever shape. It must be rectangular shape. So draw a simple rectangle will do. The simpler, the better. Yeah. Because the simpler it is, the less confusion you will get. Yeah. So okay. So of course, rectangle we have a length and a width. So let's say the length is x meter, the width is y meter. Then obviously we want to optimize the area, so we can form a relationship between the area and also the length and the width of this garden. So A is x times y. And that is not very good because there are too many variables. We try to reduce the number of variables so as to simplify the problem, isn't it? X and y, they are related because we are allowed to use only 40 meters of fence, the fencing, yeah? So the fencing is all surrounding the rectangle, and therefore the perimeter of the rectangle is limited by the length of the fencing, which is 40 meters, and the perimeter is 2x plus 2y, right? 2 times of x plus 2 times of y will give you the perimeter of the rectangle, and that has to be 40. That is the constraint we have, right? Okay? And therefore, using this equation, we can substitute back into A equal xy to get rid of one of the variable. A equal xy, and then we can get rid of y. It becomes x times 20 minus x. Because y equal to 20 minus x. If you like, you can eliminate x instead. It doesn't really matter. We just want to reduce the number of variables so that the problem is simpler. All right? So in this case, we choose to eliminate y, but it doesn't have to be like this. You can eliminate x if you want to. You end up with the same answer. So the area A changes with x. The length of the garden in this way is x times 20 minus x. Now we can maximize x. Sorry, we can maximize A. All right? So to maximize A, obviously, we want to find a critical point. So just now you learned how to find maxima and minima. So we want to find a critical point. Critical point is based on the first derivative. So differentiate once, dA dx, and equate to 0, like what we did in all these examples before the break. So differentiate once, equate to 0, you find x equal to 10 is the critical point. Only one critical point, 10. Okay? And then okay, then what happened? Is this correspond to maximum or minimum? Then we can perform the second derivative test. All right, differentiate this one more time. dA dx is 20 minus 2x, right? This is dA dx. So differentiate this one more time. The second derivative gives you minus 2. Minus 2. Minus 2 is negative. So negative, the cup cannot hold water. Upside down, you have local maximum. So this corresponds to maximum area, what we want. All right? That means when x equal to 10 meter, then we can maximize the area of this garden. All right? And of course, when x equal to 10, what happened to y? Well, it's related like by that, right? When x equal to 10, then you solve for y also 10. That means to maximize it, we want to make a square garden actually, right? With 40 meters of fencing, all right? Now, I put a note here saying that sometimes for a simple problem like this, you don't really have to do a second derivative test because common sense will tell you this must be a maximum already. This 10 meter, x equal to 10 meter, for which y also 10 meter, this is definitely, from common sense, give you the maximum area because when x equal to 10, y equal to 10, the area is either maximum or minimum because that corresponds to critical point, right? So, will that be maximum or minimum when x equal to 10, y equal to 10? Obviously maximum, common sense. Because the minimum is what? The minimum area you can make with 40 meters of fence is what? 0. You just make a very long, just make something like that. Okay. 20 meter, 20 meter, go 20 meter, 20 meter, so 20 times 2 already, 40 meter. 40 meter of fence, the minimum area of the garden you can make is 0. Definitely 0, isn't it? Cannot be negative, right? Cannot be negative, right? Common sense, area of garden cannot be negative, right? So the minimum obviously is 0, and therefore, when you work out x equal to 10, and the area will be 10 times 10 is 100, and this 100 meter square definitely is maximum. There is no need to do second derivative test, okay? But of course, if you want to do second derivative test, nothing wrong either, right? Another example, optimization. All right, this one is a geometrical application. So we have a parabola, 9 minus x squared. The shape look like this. Never mind whether we call parabola or what like that. Just a curve, just a curve, okay? And then we have a fixed point at 3, 9. x3, y equal to 9. This point fixed, right? A fixed curve, a fixed point right here. What we want to do is to find a point. Find this point on the parabola, on this line, all right, which is at a closest distance from the given point, right? So in other words, we want to minimize this, the length of this plane line, right? We want to find the point that this distance is the shortest, right? Because it's the closest, therefore the distance must be shortest, isn't it? So that means we must find an equation relating the length of the plane line with the coordinate x and y on the curve. Right? This is what we are looking for because we want to minimize the distance of the plane line. Okay? Of course, the distance of plane line will depend on which point on the parabola we are considering. Whether the point is here, or here, or here, the distance from the fixed point 3, line from this point are all different. Okay? So we want to develop an equation relating the length of this line with the coordinate x and y. Let's call the distance, the length of the line, this line is d. All right? D. Okay? So d is the distance between any point on the blue curve and also the given point 3, 9. Okay? And of course, you know the coordinate. The general point on the blue curve is xy, and this is 3, 9. So therefore, you can find the distance between the 2 points determined by this equation, isn't it? So you all know that, right? So knowing the 2 points, the coordinate of the 2 points, then the distance between the 2 points will be like that. I think this is something I talk about actually. So x1, y1 say, x2, y2, 2 points. So what's the distance between the 2 points? Your x-axis, y-axis. So you draw a rectangle, right? Sorry, a triangle. So this is x2 minus x1. This one is y2 minus y1. So the distance d is what? you use the Pythagoras theorem, isn't it? So it's the square root of the sum of the square of the two other sides, right? So here it is. So this is the equation. Okay, again, there are too many variables. D depends on x and y, depends on the x and the y coordinates, right? But we can eliminate one of them because we know that this point xy fall on the blue curve. And the blue curve is described by this equation, y equal to 9 minus x squared. So we can eliminate one of the variable, x or y. For this case, this one eliminate y, right? So y equal to 9 minus x squared, put it in, substitute inside, so this is what it is, right? And then simplify, we get an expression, the distance in terms of x. So now we try to minimize it. So to minimize it, just perform as usual. First of all, work out the first derivative. All right, differentiate this. I think this one, you should know how to differentiate. Differentiation is, I think we spend a lot of time in differentiation, isn't it? So this one you use chain rule 2 times, yeah, and the result is this. See whether you can get it. I use chain rule 2 times. So this is the first time, and this one is another time. Okay, use the chain rule 2 times. Then we get the first derivative, d prime. Sorry. Okay, then if you look at that, of course, we are going to equate d prime to 0, isn't it? Yeah, we want to find the critical point, right? Critical point, you have to equate the first derivative to 0. So the first derivative equate to 0, meaning that this part must be 0. The reason is because this whole thing here is always positive. How do you know? Well, you go as square, x minus 3 square. You take anything, square it, you always become positive. X to the power 4 definitely is positive, right? So the whole lot here is positive, and therefore it will depend on just this part. Okay? So if d prime is 0, that means this part is 0, because this one cannot be 0. So, you equate this to 0, and you solve it. You get x equal to 1, all right? And this is the critical point, and the only critical point, because the other one, 2x squared plus 2x plus 3 equals 0, will not give you any real root, all right? This part, you can only get imaginary root, and which cannot appear on the xy coordinate, right? On the xy plane, all the coordinates are real. So the only critical point is at x equal to 1. Only one, all right? One critical point. So now, you can, if you want to, perform the second derivative test to see whether this corresponds to a local minimum or maximum, all right? If the second derivative test is non-conclusive, that is to say when the f double prime, or in this case d double prime is 0, like what I showed you just now, just after the break, then you have to go back to the first derivative test to confirm whether you have a local maximum or minimum, all right? But for this case, there is no need to do so because, again, common sense will tell you the distance definitely is a minimum, isn't it? How can it be maximum? Well, maximum is very far away. Maybe this point, wow, that you see the distance is so far away. This curve going down, right? So further away, of course, the distance between the point on the curve and a given point will be larger and larger. So the maximum is infinity, actually, can be very far away. Therefore, common sense will tell you this distance, what you get, this critical point, x equal to 1, definitely correspond to a local minimum. Minimum, not minima, minimum. Okay? It's a local minimum. All right? Now, so this is what as I said, sometimes we don't have to use the second derivative test. Sometimes for simple problem like this, just like the garden problem. There's no need to use the secondary test, in fact, second derivative test. This one also the same, right? So therefore, at x equal to 1, the distance is the closest from the given point. And when x equal to 1, you can work out the y coordinate, isn't it? At x equal to 1, y equal to 9 minus x squared, this one. This one, eh? So when x equal to 1, y equal to 8. So this point is 1, 8. And 1, 8, substitute back into this expression, you get the minimum distance d from the given point. Yeah? So, and that work out to be, I think you can work out yourself. I mean, this one doesn't work out. You can substitute x equal 1, y equal 8 into the expression for d, and that represents the closest distance. But the question doesn't ask us to do that, right? It just asks to find a point. This point x and y, and therefore the answer is just 1, 8. Yeah? X equal 1, and then y become 8. Okay, another optimization problem. This case is a construction problem. We want to minimize the construction cost of a highway, all right? So what happened is this. There is already a bridge somewhere here, all right, existing bridge. And then there is an interchange, whatever, bus interchange or whatever, somewhere here, all right? In between the bridge and the interchange, we want to build a link, all right? Build a highway, all right? Link up the bridge and the interchange. And this highway has to go through this marshland, all right, marshland, and then to this the normal dry land, all right, this part. And the location of the bridge, it says the location of the interchange is 8 kilometers to the east and 8 to the south of the bridge. So you can see that this is 8 kilometers to the east, and this is also 8 kilometers. Yeah? So 8 kilometers to the east of the beach and 8 kilometers to the south of the beach. So that is where the interchange is. So we know the location of the interchange. All right? 8 meter and 8 meter. All right, so we need to build a link to it. All right? Since this is a marshland, so it will be more costly to build the expressway. All right? So for the marshland is 5 kilometer wide. So this one 5 kilometer wide. All right, this part. Okay, 5 kilometer wide, and the construction cost of the highway over the marshland is 10 million per kilometer. Okay, and for the dry land, this part is dry, so it's easier to build. The cost is lower, 7 million per kilometer. Now we want to minimize the cost. So how do we go about constructing this highway? Do we do like this? Or do we do like this? Or do we do like this? Or like this? Or even like this? We have a lot of choices. In between the marshland and the dry land, the joint can be anywhere along this line, isn't it? So where must we join the two parts of this so-called the highway, yeah, to minimize the cost, right? So that's the question, okay? So let me just get rid of those lines, otherwise very messy. This one. Okay, so that is the problem. Therefore, since we want to minimize the cost, okay, which depends on the length of the highway over the marshland and also the length of the highway on the dry land, all right? So we must find an expression, find an equation relating the cost to the total cost to the cost of the highway over the marshland and also over the dry land, all right? So let's say we construct the highway like this at a distance x away from this point, so that distance is x, all right? And therefore, this part will be 8 minus x, all right? So let's say this part is x. The joint between the two highway is at a distance x from this location, x, all right? So this will be 8 minus x, all right? And therefore, we can now formulate the equation. Okay? So the cost of the entire highway consists of two parts. The part that is over the marshland and also the part that is over the dry land. All right? The part over the marshland will be the cost per kilometer, which is 10 million per kilometer, times the length of the highway over the marshland, right? Distance across the marsh. And then, of course, the cost over the dry land will be 7. The cost is 7 million per kilometer, 7 times the distance, all right? And what is the distance across the marshland? So this is 5, right? This is x. So the length, the distance across the marshland will be this part. So from Pythagoras theorem, you know that this is the square root of 5 square, 25, plus x square. So this part. So this is the distance across the marshland. All right? And then across the dry land is the same thing. So this is 3 because the whole thing is 8. So this part is already 5. So this one must be 3. So this will be the square of 3. So 9 plus the square of 8 minus x here. And then the whole thing's square root. All right? Using Pythagoras theorem. So now we have an equation relating the total cost to the location of the joint here, right, which is x, this one, all right? So now we got to optimize this, okay? Optimize this. We want to minimize the cost. C is the cost. We want to minimize it. So what do? Okay, find this critical point. We differentiate, all right? Differentiate the critical point. I think, of course, we don't know the graph, So differentiate the critical point. I think you follow through the differentiation yourself. You need, of course, you need chain rule. Yeah, chain rule. Then you differentiate. You get this thing. All right. Simplify. Simplify it. End up with something like that. Okay. End up with something like that. So now to find the critical point, we equate the whole thing to 0, isn't it? Yeah. At critical point, the first derivative equals 0. So we equate the whole thing equal to 0, and we want to find the value of x. All right, so c prime x equals 0, and we want to solve for x. So we just want to do this. Equate this to 0, okay, this equation. So solve for x. Okay, solve for x. Well, this equation you want to solve for x is going to be quite difficult, isn't it? So one use graphical method or numerical, or maybe you can also use Newton method, right? Equate this to 0, find the roots of this equation. You can apply Newton method also, yeah? So assuming that we solved that already, so it turned out that the critical point occur at x equal to 3.56 roughly, yeah, at this point. If you want to do it graphically, you plot this graph. You plot Cx versus x. So this is Cx, this is x, and you find the intercept here. So this corresponds to about 3.56, all right? So either graphically or numerically. Of course, graphically, you cannot determine so many decimal places, all right? Okay? So let's say, assuming we solve this problem, we know the critical point. So this is a critical point. Now, what do we want to do? Do we want to carry out the second derivative test? Not really. Let me just change it. Take this out. We don't use this. I tell you why. Okay, now what we want to do is to find the minimum cost, isn't it? So the minimum cost, we don't know where. It could be like this, you see. It could be like this, isn't it? It could be like this, right? It could be anywhere, like what I drawn earlier on, right? If you look at the cost, okay, Now, this function, this cost function, Cx are in terms of x, all right? Obviously, x is the input, right? So what is the domain? What is the domain for this function Cx? What are the possible value of x? X is this distance. X can be 0, can be 8, isn't it? So x is between 0 and 8. If x is 0, then our highway will look something like this. We'll go all the way down and then come up here. So when x equals 0. When x equal to 8, if we choose x equal to 8, we have the construction will be something like this. 8, x equal to 8, right, will be correspond to this point. And then come down here like this, right? So x equal to 0 and 8 are at the two endpoints of the interval. In other words, this one is a closed interval. 0, 8, right? X can be anything between 0 and 8, including 0 and 8. And we want to find within this interval what is the minimum cost. And that minimum cost within that interval is what we define to be the absolute minimum. Absolute, ABS, absolute, it is not the local one. Remember the second derivative test? What does it tell you? It gives you the local maximum or minimum, isn't it? Local. Yeah, go back in the second derivative test earlier on. I defined there. Second derivative test gives you the local maximum or minimum. What we want to do now is within this closed interval, what should be the value of x in order to minimize Cx? Therefore, we are looking for absolute minimum. So absolute minimum, we don't use the second derivative test, right? So what we do is, I do not know which slide it is. Earlier on, I was saying that when you want to, there was one theorem which says the absolute maximum, the absolute extremum occur either at the critical point or at the two endpoints. There was one slide saying that earlier on. I think, can you identify yourself? I don't know which slide it is, right? So there was one slide earlier on we went through which says the absolute extremum occur either at the critical point or at the two endpoints for a closed interval. Therefore, to find the absolute minimum for this case, we need to find the value of the cost. We need to find the cost at the critical point and also at the two endpoints of the closed interval, isn't it? So that's what we are going to do. We are not going to use second derivative test. Okay, so that's the reason why here we work out the cost of the construction when x equals 0. Remember the closed interval there? The interval is 0, 8, a closed interval. So the two endpoints are at 0 and 8. So we have to do a comparison, right? So work out when x equals 0 at one of the endpoint, the construction cost is 110 million. How do you know? Well, substitute x equals 0 into the cost function. We know the cost function, this one. Substitute x equals 0 there, you know the cost, construction cost when x equals 0, isn't it? Do the same thing at the other endpoint, x equals 8. We can also work out the construction cost. At the other two, these are the two endpoints. These are the endpoints of the interval, of the closed interval, right? We must also work out the cost at the critical point. At the critical point, x is 3.56. So substitute this value into the cost function, Cx. Then you work out 99 million. We compare the three. Remember, there was one theorem, as I mentioned just now. The absolute extremum always occur either at critical point or at the two endpoints. So compare the three, which is the minimum, this one. 99, minimum, yeah, compared to the other two. So obviously, this gives you the absolute minimum. And therefore, this is the way the construction is to be done. So at this distance, 3.56, so if this is 3.56, then the construction cost is 99 million, which is the cheapest, the lowest cost. All right, so that's the answer to this optimization problem. Okay, then the next thing, the next application will be what is being called the related rates problem. All right, related rates problem, something to do with rates. Rate is we call it the change, how things are changing with respect to time. All right, so and of course the way how we do it is more or less similar to the optimization problem. Maybe we can look at this slide. This slide 108. Just to go through the steps first before we look at the example. Let's jump 2 slides, and I will take you back to these 2 slides. So what we do in this so-called related rates problem, the rates are related. The rates of certain different variables, they are related, and we want to find the rate of some of the variables. So what we do is make a sketch first, if you can, all right, and then establish an equation, just like the optimization problems we went through just now, and then differentiate with respect to time, and very often you need to do implicit differentiation together with chain rule. We can do an implicit differentiation, and then all the long rates and so on, we can substitute and therefore find the answer. So that's what we normally do, right? Let's go back to the slide. So let's look at this example. All right, so this is an oil spill problem. So an oil tanker, so the oil leaks out at a constant rate, 150 meter cube per minute, so the leakage, all right? And so the oil actually spread out in the shape of a circle, as you can see here. It's spread out in all directions, and then the shape is just like a circle. So the gray color is the oil spill. It covers a circle. And the thickness of the circle is 0.05 meters, so that is the depth of the oil spill on the sea, all right? And we want to find the rate at which the radius is increasing when the radius becomes 200 meters. How fast is the radius of this oil spill is changing with respect to time? So that's what we want to determine, all right? And in fact, it's quite straightforward. Of course, since we want to find the rate of the radius, that means we want to find, if the radius is r, then we want to find dr dt, yeah, the rate of change of the radius when the radius is 200 meters. And how do we relate radius? Well, we are given the constant rate of the leakage, 150 meter cube. So this 150 meter cube will determine the radius of this circle, isn't it? We know the depth of the circle, 0.05 meter, the thickness. So that is related to the volume. So from the volume of the oil leakage, then we can relate this to the radius. All right. So how do we do it? So volume is the depth times the area of the circle, the gray color circle. All right. The depth is constant, 0.05 meter. And the area of the circle is always changing with time. So it's pi times the square of the radius. R is the radius. And since the radius is a function of time, it depends on the time, so we put R comma T, all right? And therefore, the volume of the oil leak out from this tanker is V. Let's say the volume is V. So we have this V equal to the depth, 0.05 times the area, pi R squared. Okay, and we are told the rate of leakage is 150 meter cube per minute. So that obviously is V prime, dV dt, that means. Yeah? So dV dt is, as given by the question, is 150 meter cube per minute. So let's differentiate, because we need to make use of this 150 meter cube per minute. So let's differentiate. So differentiate this with respect to t. All right, so V prime, the prime denote differentiation with respect to time t. And to do that, of course, the right-hand side, we must differentiate with respect to t. To do that, we apply chain rule. Yeah, on the right-hand side, we can't differentiate with respect to t because we don't know r as a function of t. What we know is r depend on t. How does it depend on t? We don't know. We don't know this function, so we can't differentiate with respect to time. So what we do is apply chain rule, differentiate this with respect to r first. Right? And to do that, you get 2rt, right? If you differentiate this with respect to r, you get 2r. 2 times 0.05 will give you 0.1, and the r stay there. But we don't want to differentiate this with respect to r. We want to differentiate this with respect to t, isn't it? So according to chain rule, we can differentiate this with respect to r first, and then multiply to dr dt. So that's why we have an r prime here. So this comes from chain rule. All right? When you differentiate this with respect to t, you've got to differentiate this with respect to r first to obtain 2r. And then you multiply this by dr dt, so which is r prime. R prime is what we are looking for. We want to find the rate at which the radius is changing, right? Okay? So R prime is what we want. So make this the subject. So take everything to the left side. So R prime is this one. And now substitute the numbers we have. We know V prime. V prime is the rate of the leaking, which is 150 meter cube per minute. So this is 150. And we are asked to find the radius. How does the radius is changing with respect to time? When the radius is 200, so that means R is 200. So substitute 200 there, and use your calculator, you get 2.39 meter per minute. So that is how fast the radius is increasing when the radius is 200. Okay? If the radius is not 200, then this will not be 2.39, because this will obviously depends on R, as well as depend on how much oil is leaking per unit time, V prime. Yeah, depend on V prime as well as R. Okay? I mean, it's just a simple example, but nevertheless, it shows you how differentiation is applied. Okay, another question. So this one is a cross junction. All right. So this is the car you are driving. You are in a blue car. You are traveling at 50 miles per hour in this direction. All right, and you are at half mile north of the intersection. Maybe I just write down here. So this is the x-axis, this is the y-axis. And this is where you are. You are driving the blue car. You are at half mile from the junction. All right, at that moment, that's a distance. And then on the other side, there's a police car, checking on you, the red one. So the police car is traveling to the left side at a speed 40 miles per hour. And also, it is at a distance a quarter mile from the same intersection. So this one is 1/4 of a mile. So that's what happened, all right? At that instant, the police car has a radar. Is checking on you, is measure the distance between your car and the police car. All right, how far is this radar can tell the rate of change of the distance between your car and the police car. And then what we want to do is what does the radar register? How many miles per hour? Yeah, how many miles per hour is the distance between your car and the police car. Okay, so this is a rate problem. And the rate of change of the distance between the two cars is, of course, related to the velocity of the two cars, isn't it? So the rate is related to other rates. So we call this related rate problem. All right, now, of course, since we want to find what does the radar register, and the radar actually measures the rate at which the distance between the two cars is changing. So that means it's measuring this distance, right? The rate of change of the distance between the two cars. And this one we can use, because these are the roads are at a right angle, this is a right angle. So again, using the Pythagoras theorem, we can relate the coordinate of the police car and your car with the distance, isn't it? And then we try to do something about it, yeah? So the distance between the cars is x squared plus y squared, and then the square root of the 2. Remember, this is the y coordinate, this is the x coordinate. And therefore, the distance between the two cars is obviously the square root of the sum of the two squares, right? This distance, the police car is at a distance x from the intersection, while your car is at a distance y from the intersection.